Till now, we have seen multiple questions on how to construct minimal finite automata that accepts strings over A's and B's, where we had constraint over number of A's, constraint over number of B's, and even constraint over the number of symbols in the string, the complete string, right? Now let's look at a different question, an interesting problem, where we will be constructing a minimal finite automata that accepts all binary strings whose integer equivalent is divisible by 2, right? Here we were given with binary strings, so each string is of binary number. That means the input alphabet is of zeros and ones. Each string is made up of zeros and ones, right? And the integer equivalent of that string is divisible by 2. Now let's look at what are all number systems we have other than this binary number system, right? We have number systems like unary number system, binary number system, ternary number system. Then there are octal number systems, octal number system, then decimal number system, and hexadecimal. These are the popular number systems through which we can represent any number, right? In unary number system, we have only one symbol. This is the only symbol which we can use to represent any number, right? So if we want to represent number 2 in unary, let's say this is in decimal, and we want to represent the same number in unary, we need to write like this: 1 1 2 times. This is unary, right? If you want to represent 3, which is in decimal, in unary, we need to write 3 ones to represent 3. If you want to write 4 in decimal, which is in decimal in unary, we need to write 1 4 times in unary system, and so on, right? So if you want to represent 100, which is in decimal in unary system, you need to write once 100 times. This is 100 times. In unary system, right? This is how you represent integers in unary number system. Now coming to binary number system. In binary number system, we have symbols. We have two symbols, 0 and 1, right? We have two symbols here. We have only one symbol here. In ternary number system, we have symbols 0 1 2. There are three symbols here in ternary, right? In octal, we have 8 symbols, 0 1 2 so on till 7. There are 8 symbols here. In decimal decimal number system is the most popular number system we have in general. So in this we have 10 symbols, 0 through 9, right? There are 10 symbols. In hexadecimal system, we have 16 symbols, 0 1 2 so on till 9, and from A to F. These are 16 symbols which will be in hexadecimal number system. We can represent any number in any of these number systems, right? We have seen how to represent a number in unary, right? Let's see how to represent an integer in binary number system. Let's say we have number 4 and we need to represent, this is in decimal, and we need to represent this number in binary. So what to do? We will divide this number by 2. 2 divides 4 2 times, so leaving a remainder 0. 2 divides 2 1 time, leaving a remainder 0. So the binary representation of 4 is 1 0 0. You need to write like this in this order: first 1 0 and then this. So this is how we represent 4 in binary number system. Let's say we want to represent number 7 which is in decimal in binary number system, right? So what we do, we divide number 7 by 2. Why do we divide any number with 2? Because 2 is the base of binary number system, right? Here for unary number system 1 is the base. In ternary it is 3, in octal it is 8, in decimal it is 10, in hexa it is 16, right? So we need to divide by 2 in case we want to if we want to represent any number in binary number system. So 2 divides 7 3 times, leaving a remainder 1. 2 divides 3 one time, leaving a remainder 1. 7 can be represented by 111 in binary number system. Let's consider the reverse. I mean, let's say we were given with the binary number 111 and we need to convert this to decimal number, right? We don't know what the decimal number is. We need to find what the equivalent decimal number given the binary number. How do we convert? So we take the binary number and we give the positions. This is 0th position, this is 1th position, this is 2nd position, right? So we will multiply each number with the corresponding powers of 2's, right? So it means 1 into 2 power 2, this 1 into 2 power 2 plus this 1 into 2 power 1 plus this 1 into 2 power 0. Why are we multiplying with powers of 2's? Because the base here is 2, right? So we need to multiply each digit with 2 powers of 2's. The power of 2 will be the position, right? 2 1 0 are the positions of each digit. So this is 4 plus 2 plus 1, it is 7. So this is in decimal number, right? This is decimal. Let's take another example. Let's say we need to find the decimal equivalent of 1001, which is our binary number, right? We need to find the decimal number. So how do we do that? We take the binary number 1001 and give the positions from left to right. Leftmost digit will be our 0th position, and right, and the next position will be 1, and next is 2, next is 3, right? So these are the positions and we multiply each digit by the corresponding power of the position, right? So this will be equal to 1 into 2 power 3 plus 0 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0, right? So this is equal to 8 plus 0 plus 0 plus 1. This is equal to 9. So 1001, which is binary, is equivalent to 9 in decimal, right? This is how we convert one number system to another number system. Convert a digit from one number system to another number system, right? Now let's come back to our problem. So here we were asked to construct a minimal finite automata that accepts all binary strings whose integer equivalent is divisible by 2, right? So the given input alphabet is 0 and 1, and each string should be from 0 and 1, where the integer equivalent of the string W is divisible by 2, right? So in other words, we can write it as integer equivalent of W is congruent to 0 mod 2, right? We have seen similar to this question, right? Like constructing minimal finite automata for strings over A's and B's, where number of A's is divisible by 2 or number of B's divisible by 2, right? So in the same way, this is a a bit different question in which we were asked to look at the integer equivalent of the binary strings. First, let's consider all the numbers which are divisible by 2. So the numbers are 0, 2, 4, 6, 8 and so on, right? So the binary strings corresponding to these numbers will be in our language. So what are all the binary strings? 0 corresponding to 0. This is 1, 0. These are all binary numbers. These are all integers, right? So the binary number corresponding to 4 is 100. For 6 it is 110. For 8 it is 1000 and so on, right? All these strings are in our language. This is our language. L is equal to 0, 10, 100, 110 and so on, right? Now let's look at the strings which are not in this language. What are all the strings which are not in this language? The strings which the binary strings whose integer equivalent is not congruent to 0 mod 2, right? It means when we divide integer equivalent of the string by 2, if it gives a reminder 1, then this is not in the language, right? That string will not be in our language. So what are all the strings which are non-divisible by 2? Those are 1, 3, 5, 7, 9 and so on, right? All these are odd numbers, right? If you see, these are all the even numbers and these are all odd numbers. So the strings which are corresponding to these binary strings which are corresponding to these integers are 1, this is 1 1, this is 101, this is 111, this is 1001 and so on, right? If you see, the strings which are in the language ends with zeros, right? And the strings which are not in the language end with 1, right? All these strings end with 1 and these are not in our language. All these strings which are ending with 0 are in our language, right? So this is one observation. So with this observation we can start drawing the DFA for accepting this language. Let's first write the complete language, the list of strings which are in this language. So the strings like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, all these are in this language, right? The strings of length 2 like 0, 0 and 1, 0 are in this language. The strings of length 3 like 0, 0, 0 or 0, 1, 0 or 1, 0, 0 or 1, 1, 0, all these are in this language. The strings of length 4 like 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0 and so on, all these are in this language, right? So all these strings are ending with 0. With this observation, let's try to construct a DFA. Let me quickly write the language here so that it will be easy for us to draw the DFA. So clearly epsilon is not in this language, right? Epsilon is not in this language, so our DFA will not have initial state as final state, right? So let's say A is our initial state, and since epsilon is not in our language, this is not our final state. On seeing the minimal string, let's say this is the minimal string, and seeing 0 from A, we go to state B and accept it because 0 is in our language, right? On seeing 1 from A, I will be in this state only no matter how many ones I see, because I don't consider, I'm not bothered about the number of ones or its position, because I just look at 0, and if it is at the end of the string I will accept it, right? So I don't care about the number of ones in the string. So I will be in A on seeing 1, right? So what if I see a 0 at B? Like, how did I reach B? I reached B on seeing 0, right? What if I see a 0 at B? This is still a valid string and it is in the language, right? So no matter how many zeros I see, I will be in 0, I will be in B itself, because I have already seen a 0 and I can still accept this string because this is anyway ending with 0, right? So no matter how many zeros I saw, I'll be in B itself, right? What if I see 1 here at B? So how did I reach B? On seeing 0, right? So on seeing 1 from B, I will go to that state from where I hope I can see 1 1 0, and I will accept this string. If I have 1 at B, I should not accept this string, right? This, because this is not in our language. So I will wait for 1 0 to occur after seeing 1, and then I may accept it if it ends at 0, right? So such a state is A, and I will go to A on seeing 1, right? So I can see A is complete, it has transitions over 0 and 1, and B is also complete, it has transition over 0 and 1. So this is our DFA. Is this the minimal DFA? Yes, we cannot reduce the number of states than 2, right? So this is our minimal DFA also. So we draw this DFA keeping in mind that every string is ending with 0, right? Now the question is, we need to consider all the strings, all the binary strings whose integer equivalent is divisible by 2, right? But we have found a pattern that each string is divisible by 0, and we have constructed a DFA, right? So let's construct a DFA based on the given question, right? So now the given question is, we need to construct a DFA for all binary strings whose integer equivalent is divisible by 2, right? So let's say, since it is integer equivalent of W is congruent to 0 mod 2, so each number should be divisible by 2. So what are all the possible reminders when we divide a number with 2? So it is 0 or 1, right? So these are the two possible reminders when we divide a number with 2. So there will be two states, Q0 and Q1, right? So 0 corresponds to Q0 corresponds to all the states, all the strings which leave a remainder 0, and Q1 corresponds to all the strings which leave a remainder 1. We have classified all the strings into two classes. One is the binary strings whose integer equivalent is divisible by 2, and the binary strings which are not divisible by 2, right? This leaves all the strings which leave a remainder 0, and all the strings which leave a remainder 1, right? So how do we draw the transitions over each of these states? Now let's consider the minimal string. This is our minimal string, right? 0 is our minimal string, and this is in our language. So on seeing 0, or any number of zeros for that matter, I will be in Q0 itself, because when we divide this number with 2, it leaves a remainder 0, right? So no matter how many zeros I see, I will be in Q0 itself, right? On seeing 1, if I see a 1 at Q0, the remainder when we divide 1 with 2 is 1. So I go to Q1 on seeing 1, right? So Q0 is complete. Now at Q1, if I see a 0, so how did I reach Q1? I reached Q1 on seeing 1, right? If I see a 0, the integer equivalent will be 2. When I divide 2, it leaves the remainder 0. So if I see a 0 from Q1, I will go to Q0, right? What if I see 1 here, 1 at Q1, like this? So the integer equivalent of 1 is 3. When we divide 3 with 2, it leaves a remainder 1. So the state corresponding to remainder 1 is Q1 itself. So I will be in Q1 on seeing 1, right? If you take any other number like 1011, what is the integer equivalent of 1011? 11, right? 11 is not divisible by 2. 11, it leaves a remainder 1, right? So let's consider how this guy, this 1011, is parsed with the given DFA. So starting at Q0, on seeing 1, I will go to Q1. From Q1 on seeing 0, I will go to Q0. On seeing 1 at Q0, I will go to Q1. On seeing 1 at Q1, I will be in Q1 itself. Since we are done with the string, I will be in Q1 and I say I have remainder 1, right? This Q1 is corresponding to the remainder 1 and Q0 is corresponds to remainder 0, right? So this is our DFA, and we can say Q0 is our final state, right? So I can see Q0 has all the transitions over zeros and ones, and Q1 has transition over 0 and 1. So we can say this is DFA. So let's draw the state transition function, state transition table for the corresponding DFA, right? Every finite automata can be represented by either a state transition table or state transition diagram. This is diagram, and we shall write the table now corresponding to this DFA. So the transitions are over zeros and ones, and what are all the states we have? Q0 and Q1, right? This is our initial state, and Q0, on seeing 0, I will be in Q0 itself. Q0, from Q0 on seeing 1, I will go to Q1, right? From Q1 on seeing 0, I will go to Q0. From Q1 on seeing 1, I will be in Q1 itself, right? This is our state transition table. But there is a small pitfall here in this DFA, right? Can you observe it? Just pause this video and think what is the pitfall here. Just compare this DFA and the DFA which we have drawn earlier. This one. Compare these two and you will understand what is the difference, right? So if you observe, this DFA is accepting epsilon, right? Since our initial state is final state, we accept the epsilon which is not in our language, right? So this is not correct, right? So it is, so to eliminate the epsilon, we need to introduce one more state. Let's say this is QS. This will be our initial state, and what are the transitions over zeros and ones from QS? We need to go to q0 on seeing 0, and we go to whatever state q0 is going to on 1, right? So q0 is going to 1, going to q1 on seeing 1. So we go to q1 on seeing 1, right? We just add one more state qs, so that epsilon is not in our language, and we make q0 as not a non-initial state and qs as our initial state. So this is our DFA. Let me write it again. Let me draw the DFA again. q0, this will be our final state, and q1, this is a new state qs, and there is a transition over 0 from q0, and this is our initial state. On 1 it goes to q1, and on 0 it goes to q1 to q0, and from 0 and from qs on 0 it goes to q0, and on 1 from qs to q1. On 1 we have we have a loop over q1. So this is our DFA, right? This is our initial state, qs is our initial state, and q0 is our final state. And this does not accept epsilon, and it accepts all the strings which are in this language. So this is the DFA, which accepts all the binary strings whose integer equivalent is divisible by 2, right? Now the question is this the minimal DFA? So from qs we are going to q0 on seeing 1, on seeing 0, right? And from q1 also on seeing 0 we are going to q0, right? Let's say I'll just write it, qs on seeing 0 we are going to q0, and transition from q1 on seeing 0 we are going to q0, right? So these are fine, these are equivalent on seeing 0. Now let's see transitions over 1. From qs on seeing 1 we are going to q1, right? And from q1 on seeing 1 we are going to q1, right? So on seeing 1 we are going to q1 itself from each of these states, right? On seeing 0 we are going to q0 itself from each of these states. So we can say that these two are equivalent. So q1 is equivalent to qs, right? So there is no need to have qs separately. That means we can merge q1 and qs, right? Let's say the new state is q1s. Now let's draw the DFA after merging q1 and qs, right? So our initial state will be q1s, and the other state is q0, right? So on seeing 0 I will be going to q0, right? On seeing 1 I will be going to q1, which is equivalent to qs. Now since we have merged, this is equal to q1s. So on seeing 1 I will be in q1s only, and the transitions over q0 will be intact. On seeing 0 we will be in q0, on seeing 1 we will go to q1s. This is our minimal finite automata for strings of binary over zeros and ones whose integer equivalent is divisible by 2. Now compare this minimal finite automata with the DFA which we have drawn earlier. This one, right? These two are equivalent, right? These two are same. Just the state names are different, but everything else is same, right?